functions, then train our model, that is a quantum SVM, to fit the sample data, finally predict it. So here in the previous K nearest neighbor, I have used QuizKit library, which is a part of IBM. Here we are using PennyLane, which is also a powerful quantum computing machine learning frameworks. The first thing is we need to import all the supporting libraries. First, install pip install PennyLane. After that, import PennyLane as a variable. Then the data sets from OpenML, we are going to fetch the data set, or else in from our local machine also we can give the data set. As of now, the MNIST data set is available in OpenML, so therefore we are using this one. Then here in MNIST dataset is a dataset for character recognition, and it has 10 classes, 0 to 9 classes. So in our application, just we are going to convert that multi-class problem into binary class. So we are concentrating only two class labels. It will recognize only two labels, 3 and 6 or something else. So for filtering out and also for decomposing, we are using PCA. Then this one already train test split for splitting our training data and also testing data. We can use this one. And for pre-processing, conversions, shifting, everything. Then SVM, that is quantum, sorry, support vector classifier, so that we are importing. Then all the metrics, whatever metrics, and this is for numeric Python, that is numeric operations, and this is for plotting. First we are going to load the data set. So here nmist, that is fetch from that particular data set. Here the mnist is having 784 features, so this is the label of that one. Then this is the first version, and we are giving the data to x and the target to y. So we are splitting input variable as well as the target variable. Input and output variable are dependent and independent variable. So x is the input variable, y is the output variable, target. And I already said that instead of going for a multi-class classification, here in this case only two classes are taken. So therefore we are filtering two classes. Here in this example we are taking only 3 and also 6, and so therefore we are taking the mask, and that particular data are filtered out. And for 3 it is assigned as 0, and for 6 it is assigned as 1. So all the target values are assigned as binary classification, 0 and 1. For the tuples or the records which is having 3 as 0, and the data which is having a 6 is represented as 1. Then we are applying the feature dimension reduction, reducing the feature dimensions by means of principal component analysis. So number of components is equal to n bit. It is how many qubits we are going to use in our case. So why? Because we need to map all the uh, input values or the features in terms of qubits. Okay, so here 784 features are there. So our qubit is only 2 power 5. So that that mapping had to be done. So instead we are reducing the features by means of principal component analysis, and based on that number of components will be selected with the number of qubits what we are going to assign. Then we are transforming that one, that filtering that one. And here this is a pre-processing, normalizing all the input features into a scalar and transforming it. This is for testing, splitting the training and testing. Here 20% is used for testing and 80% is used for training. And here our qubit representation is 8. Therefore 2 power 8 possible values can be, features can be mapped or at a time. So this is the representation. So qubit mapping feature, quantum feature mapping. So in this case, we are assigning 8 that is mapped with the principal component and a number of components we are taking. 2 power 8 components we are taking, and this is creating or taking the simulator QML dot device qubit default device, and the number of wires is 2 power 8. Okay, we need to connect 2 power 8 input samples, isn't it? So therefore the wires is equal to 2 power 8, and this is the node for creating. You are passing this one to create a quantum instance, and next we have to mention the encoding part. So here they are using angle encoding, x1, x2, and x1 is passed along with the wires number of qubits. Based on that it will be encoded. Then x2 is also encoded. Then it will return that value. Then quantum kernel is defined. So this is a matrix. So this is also with the A and B, the matrix, what kernel matrix we are using, number of qubits it will be mapped. Next, we are assigning to the SVC, support vector classifier. Class kernel is the kernel matrix. So that is given as SVM. Then we need to load the data set, and we need to assign that one extrain, testing, training. So this is number of qubits. And next we need to perform training, that is svm dot fit of x train y train. Okay, so here in this case we are using normal svm classifier on quantum data, whereas in the previous case we are using quantum algorithms, quantum knn for the quantum bits. Then once it is performed, the training is performed, we need to predict that one. So predicting the X test, and finally you can calculate the accuracy or other metrics. So this is SVM kernel, number of samples, maximum sample 100. And this we are mapping with the kernel. Finally, we are going to plot the class indices, arrange that one, and we are plotting all the metrics, number of samples, accuracy, and number of samples, training samples, accuracy, etc. So that's all about SVM classification. I just show this one in Google Colab. You just use Jupyter Notebook or Google Colab or Anaconda, Spider, anything, or any Python prompt, VS Code itself, we can execute this one. Sweta, your question is, can this quantum machine learning replace the traditional machine learning? It's not replacement, just enhancing the traditional machine learning process. So with the quantum computing, we are giving the computing increased computing facility to optimize it. So is the quantum machine learning? Yes. Why? Because there are some simulators are available with IBM, with Google. So they will offer it for free. The frameworks also available. You can try your own data with this machine learning. So I have shared this one. So this one I have Just wait. The same thing I have implemented in Google Colab. So installing the Penny Lane framework. For that, I'm executing this pip install Penny Lane. Already yesterday itself, I have uh, done this one, executed this one, and then we are importing the Penny Lane QML. Then whatever thing I have shown there, we are creating a quantum instances by means of QML.device, and then we are defining the circuit. So here they are using the basic embedding, that is basic encoding. There are three types of encoding: angle, basic, as well as uh, amplitude. So basic encoding. So that circuit is shown here. And this is the second type of encoding, amplitude encoding. And also we are creating the quantum circuit. So the quantum values will have both real and also imaginary values. Then this is for angle embedding. Okay, so now comes to this part, that is uh, SVM classification. So here we are using this one, all the libraries we are importing here, and then we are loading the MNIST dataset with 784 features, and filtering only two classes instead of using multi-class, so that we are performing masking. Then we are assigning that components, all the features, 784 features are reduced to number of qubits. Here we have used a number 2 power 8, so that number of qubits, based on that the input is mapped, the feature should map. So therefore we are reducing that one, and we are equating this one, and then splitting the x as well as x training, x filing, using the data sets, number of qubits, defining the device, also number of wires for that particular thing. And here they are using angle encode embedding. This is a kernel matrix. So then we need to perform this, the one that is fitting our model. After fitting it takes more time. So yesterday I have started, but it is not completed. So there is a thing. Uh, we can use your own small data set, and then you can try it for a bigger one. Finally you can perform the displaying all the plots. So this is one thing, and next one is QANN. Just I'll stop the previous one, and I'll share the next screen. So this is quantum artificial neural network. So this is from QuizKit, which is a product, a framework of IBM. We install QuizKit. That is the first step. Install that particular framework, and then you are importing the quantum circuit. Then for plotting visualization, that even that is also available in QuizKit. Then for plotting, and then creating the quantum circuit with one qubit and one classical bit. Then you are creating a gate Then this is the measure. We need to measure that one. This is for display purpose. So we are measuring that particular thing and we are giving 0 0 for that one. And so therefore for this circuit we'll get 0. So here for me that AER simulator is not imported. This is the way where we can create the quiz kit quantum computers or instances for our computing purpose. So Quiskit, there is some problem. So again, I will move on to this penny lane. Quantum circuit, the classifier model. So this is a variational classifier. The weights, bias, XY values of neural network is assigned. Then the seed value, number of layers, number of qubits, and number of rotation parameters. And specify the optimizer, number of iterations, evaluate the test result. So this is our test accuracy. For every 10th epoch, I have displayed the accuracy. So here randomly we are selecting the data instead of taking the real data set. This is the input data we have supplied, and with that input data, we have applied the neural network to classify, to perform the classification. So the questions are, is there any different methods encoding classical data? Yes, there are three methods are available. One is basic encoding, amplitude encoding, and angle encoding are there. Any other questions? And these are the challenges in quantum machine learning. Now we are using noisy intermediate scale quantum, so therefore it limited the number of qubits as well as noise. And I have already said that there is a flat surface also. For that also they will calculate the cost. And data encoding is a major problem in quantum machine learning. Why? Because we are converting classical data to quantum data, so that is a problem. Then algorithm scalability, it is under development, so they will perform so far uh, the performance wise, that is accuracy wise, there is no the researchers are very few. Only based on time complexity, only they have given the thing. So this can be done in future, and they can use propose many articles. Any questions? So with this, I'll end the session. If you have any questions, please put it in the chat window.
Dear participants, if you have any questions or queries, kindly post them in the chat box. Otherwise, kindly mute your mic and ask them.
There is no more question. Shall we wind up the session?
Yes, ma'am. Yes.
Wait, ma'am.
Thank you very much, ma'am, for your insightful and thought provoking session. We truly appreciate the way you have connected quantum computing with real world applications in machine learning. Your presentation was both informative and inspiring. On behalf of the organizing committee, I express our sincere gratitude for taking the time to be with us today and enriching us with your expertise. I also thank all the participants for your active engagement throughout the session. Let's reassemble tomorrow for the final day of our FDP with another exciting session. Feedback links has been posted in the chat box. Kindly fill it. Have a great day ahead. Thank you once again.
Thank you all for the patient listening. Once again, I thank all the organizers and providing me the opportunity to present here. Thank you.
Thank you, ma'am.